Welcome to this talk on classifying continuous constraint satisfaction problems. This talk is based on a paper by Miltzow and me. But before talking about continuous constraint satisfaction problems, I first want to say something about packing. So consider a problem where we are given some polygons in the plane and also a square container, and we ask, can we fit all these polygons into this square by just rotating and translating the pieces? This is quite a fundamental problem in computational geometry, and for a long time it was unknown whether it was what its complexity was. It was known to be NP hard, but quite recently Abrahamsen, Miltzow and Seiferth proved this problem to be ER complete, so complete for the existential theory of the reals, and I will get into what that means in a minute. But now consider this even simpler problem where we only allow convex pieces. So arguably this problem is even more fundamental than the previous problem. However, unfortunately these methods used by, or the framework used by Abrahamsen, Miltzow and Seiferth did not they did not manage to extend those results to also include this new case. So they did not manage to prove that this problem is also ER hard. However, using our results, we were able to extend their framework to also show this fundamental problem to be ER complete. Okay, so before I will say what exactly our results are, let me introduce this complexity class ER, or complexity class of the existential theory of the reals. And to define this class we need a problem which is also called existential theory of the reals, but it's abbreviated as ETR. And in this problem we are given some formula involving some real variables, and we ask, is there some way to assign a real value to each of these variables such that this formula is satisfied? Now we say that the problem is in this complexity class ER if we can reduce it to this ETR problem. And we can also define ER hardness and ER completeness, and where basically something is ER hard if ETR can be reduced to this problem. Now it is the case that MP is contained in ER and ER is contained in P space. So this first inclusion is not that hard to see actually, but the second inclusion is highly non-trivial. And it is also conjectured that all these inclusions are strict, but so why are we interested in this complexity class? Well, it turns out that a lot of interesting problems in computational geometry are complete for this complexity class. So for example, recognizing line segment intersections graphs is ER complete. So we're given some graph and we ask, is there some set of segments, one per vertex, such that two segments intersect, even only if there's an edge between them. Also the art gallery problem is ER complete. So given some polygon, what's the smallest number of guards to guard the whole polygon? And also, as mentioned before, a lot of packing problems are ER complete. And one nice thing, if you know that a problem is ER complete, is that you now also know that a lot of tools which are usually used for NP hard problems cannot be applied anymore. So for example, ILP solvers and set solvers cannot really be applied to these problems because you can only apply them if your problem is also contained in NP. But how do we prove that such a problem is ER complete? And actually proving that a problem is contained in ER for these problems, it's not that difficult, or at least it's not the most difficult part of the proof. But proving that a problem is ER hard is a lot more difficult. And usually some intermediate problems are used for this. So you want to give a reduction from ETR to your problem, but we have some intermediate ER complete problems. For example, this ETR conj, where instead of allowing any formula with these real variables, we only allow some conjunction of a set of constraints, where each constraint is of one of these two forms. So either it is some polynomial constraint, where some polynomial expression in some of the variables is 0, or it is a constraint of the form some variable is at least 0. And every ETR formula can actually be written in this way. So also this problem is still ETR complete or ER complete. But we can simplify this even further to, for example, ETR AMI, where we replace these polynomial constraints to only allowing polynomials of very specific forms. So we have this addition constraint, this multiplication constraint, and we also still have this inequality constraint and some extra constraint. And this is still ER complete, basically because every problem can be, or every polynomial can be written using just additions and multiplications. And from this problem it already becomes maybe a bit clearer how to prove that some kind of geometrical problem is ER hard, since we basically need to encode, have some way to encode variables in our geometrical problem, and then we need a gadget for each of these 4 constraints. But still, it is easier said than done, and especially this multiplication constraint, which is also the only nonlinear constraint of the 4, is usually the hardest to enforce using some gadget. So luckily we can simplify this problem even further. So for example, there's this ETR square problem where this multiplication constraint, which involves 3 variables, can be replaced by an even simpler constraint, so a squaring constraint involving only 2 variables. And it turns out this is also ER complete. And similarly we have this ETR inf, where we have a different nonlinear constraint. And all these problems on this slide are actually called continuous constraint satisfaction problems. So these are problems where where an instance consists of some conjunction of constraints, where every constraint comes from some very limited set of constraints. And now a natural question to ask is, okay, but what if we replace this nonlinear constraint, which is usually the hardest constraint to implement in a gadget? What happens if we replace this constraint by some completely different constraint? So what happens in general? Is it in general still ER complete, or will it be simpler? And this is the question that we answer in our paper. And we do this by showing that a lot of these problems are still ER complete. So in particular, we first study this curved equality problem, where we have replaced this nonlinear constraint by some general constraint of the form f of x comma y equals 0. And now we show that in a lot of cases this problem is ER complete, but for this f should satisfy some conditions. And in particular, if you look at the 0 set of f, then this should define a smooth curve through the origin. And furthermore, we need this curvature in the origin to be non-zero. So this is what we mean by curved. So in a sense, it should be sufficiently nonlinear. And we show that if these properties are satisfied, then our problem is ER complete. Now we generalize it even slightly further by looking at this convex-concave inequality problem, where instead of this single equality, we have 2 inequalities. And we show that if these inequalities also satisfy certain conditions, then this CCI problem is also ER complete. So what are these conditions? Well, again, we need both f and g to define some curve through the origin with non-zero curvature. But note that if you have such a curve, then this basically divides the region around the origin into two regions. So one where f is positive and one where f is negative. And because this curvature is non-zero, one of these regions will be basically convex around the origin if you restrict it to some small ball around the origin, and the other one will be concave. And now what we require is that one of these inequality conditions encodes such a convex condition, and the other one encodes such a concave condition. And if this is satisfied, then our problem is also ER complete. So how does this relate back to the packing problem, which I mentioned at the start of the presentation? So in this paper by Seiferth, Miltzow, and Abrahamsen, they proved this packing problem by having a number of gadgets, but for this nonlinear constraint, they use this ETR-inf problem where we want to enforce a constraint of the form x times y equals 1. And for this they needed two gadgets, one for enforcing x times y is larger or equal to 1, and one for enforcing that the product of two variables is smaller or equal to 1. And the gadgets themselves are not that important now, but what is important to note, but by combining these two gadgets you can enforce such an equality constraint. But also note that this second gadget, it involves a polygon which is non-convex, which is also why their construction fails for when you only allow convex polygons. But now using our results, we can basically drop this second gadget and try to replace it by some completely different gadget which still enforces some concave condition, because this condition is also concave. And because of our new result, it doesn't have to be of this very specific form. The constraint enforced by this gadget doesn't have to be of this very specific form, x times y is smaller or equal to 1, but we can use any constraint. And this allows for a lot more freedom in constructing this gadget, and therefore this also allows us to complete this proof. Okay, so for the rest of this presentation, let me give a sketch of some of the main arguments used in the proof. So, and I will only do this for the first theorem, so where we have this curved equality problem. So the idea is basically that we make a reduction from ETR square, so the problem with this squaring constraint, to our new CE problem, so this curved equality problem, where we have this more general constraint. But before we perform this reduction, we replace the CE problem by some very similar problem, or actually equivalent problem, which resembles this squaring problem a bit closer. So, and the way we do this is first by taking this nonlinear constraint and then using the implicit function theorem to, in a neighborhood of the origin, write this in an explicit way. So we take some function g such that this condition is equivalent to this previous condition around the origin. It should, however, be noted that even if this f has some very nice form, so for example it's a polynomial, then it might be the case that this g does not allow a closed form, but this is not important for the argument. And now we can basically look at the Taylor expansion of this g, and note that we required this f to be curved, so we want its curvature in the origin to be non-zero. And what this means about g is that the second derivative of g is non-zero. So its Taylor expansion has a non-zero coefficient before x squared. And now by subtracting some linear polynomial from g and rescaling it a bit, we can ensure that this g actually very closely resembles squaring. And in this way we get this equivalent problem, CE explicit, where this implicit constraint from the previous slide is now replaced by this constraint of the form y equals g of x, where this g is furthermore scaled in such a way that that it very closely resembles squaring. Okay, so now how do we perform this reduction? Well, the first idea is to take epsilon to be some very, very small number. So actually it's doubly exponentially small in the description complexity of phi, which is our ETR square formula, which we are reducing to this new problem. And why do we do this? Well, it turns out that if we take this ETR square problem and we replace each of these squaring conditions by some slightly relaxed conditions, so we allow this error basically in the squaring condition to be at most epsilon, then because this epsilon is so very, very small, somehow this new problem will be equivalent. So what does this mean? Well, by allowing some slack in all these squaring conditions, it might of course be that we add some extra solutions to our problem. However, it turns out that if this original problem didn't have any solutions, then this new problem also won't have any solutions. So in that sense, it's still an equivalent problem. Okay, so how do we use this observation or this fact? well, we start with this phi basically, so this ETR square instance, and we scale down all variables by epsilon, or actually we want to ensure that every variable is an absolute value at most epsilon. And then we, on this scaled down variables, we approximate these squaring conditions by just using g. However, this squaring a variable and applying g to a variable is not exactly the same. So for this reason, we need to add some slack to these replaced conditions. So why is this new instance equivalent to the original instance? Well, the idea is if you have some solution to this original ETR square formula, then the error in which occurs because we replace squaring by applying g is smaller than the slack we add. So any solution to this original problem will still be a solution to this new problem with this slack. And the other way around, it turns out that if you choose all the slack appropriately, then if you have a solution to this new problem, and it will actually be not a solution to this exact squaring instance we started with, but it will be a solution to this relaxed squaring problem, where every squaring constraint is relaxed a little bit. And because of that, this new problem will still be equivalent to this original problem. Okay, so this is all I wanted to say about this, about the proof of our results. Well, actually, one more remark is that this second theorem with this convex-concave inequality problem, I want to say that this proof here is actually very similar to this proof of this first theorem, but there are just a lot more details. Okay, so with that I would like to end. Thank you for your attention.